as we begin to talk about the reactions of the aldehydes and ketones, we need to take a look at the reactivity trend for carbonyl compounds in general, and specifically where the aldehydes and ketones fall in this trend. So here is the aldehyde and the ketone in this series, and that's kind of our focus, but we want to apply it along with the other carbonyl compounds. Basically, what we're asking here is how susceptible is the carbonyl toward nucleophilic attack? So we're thinking about adding a nucleophile with a negative charge to the carbonyl carbon. So what's going to be most attracted to a nucleophile is something that's positively charged. So that means more positive character on the carbonyl means it's going to be more reactive to the nucleophile. So what we're going to do is look at these carbonyl compounds and analyze them for both inductive and resonance effects to see what makes things more or less reactive. And I already have them listed here in order of reactivity, and the carboxylic acid derivative series is kind of broken up with the aldehyde and the ketone in the middle. Amides are the least reactive, moving up to the esters and carboxylic acids. Then we have our ketone and aldehyde, finally anhydride and acid chlorides, which are the most reactive. So let's look up here at the top end where we have the most reactive carbonyl compounds. So why are the acid chloride and anhydride carbonyls so reactive towards a nucleophile? Well, the reason behind this is primarily electronegativity of the attached group. So this Cl here, that's an electron withdrawing group. It's pulling electron density away from the carbonyl compound, and that's putting a lot of partial positive character on that carbon. If it has a lot of partial positive, then it's going to be attracted to the nucleophile. With the anhydride, we can kind of think about either of the carbonyl carbons. Let's just focus on this one as being the one that's attracted to the nucleophile. So we have the oxygen, which is an electron withdrawing group. But what makes it so different than the ester and the carboxylic acid that are clear down here? Well, the reason is the lone pairs on this particular oxygen, those are kind of tied up on the other side in resonance. So if we have electron density kind of going like this, that's allowing a lot of partial positive character on that carbonyl. So we're going to say up here with the most reactive species, inductive withdrawal by the electronegative atom. Now let's jump down to the left-hand side where we have the least reactive carbonyl compounds. So why is the amide so unreactive? Well, we have lone pairs on the nitrogen, and those lone pairs are pushing electrons toward the carbonyl carbon in resonance. So there's a lot of electron donation there. Likewise, on the ester and the carboxylic acid, we have the same thing. So that electron donation puts a lot of electron density onto that carbon, making the carbonyl carbon less partially positive. Now, we'll look at the aldehyde and the ketone. They kind of fall in the middle. So there's no big resonance donating groups attached. There's also no electronegative atoms attached, which is why they kind of fall here in the middle. So in terms of the effects, there's purely inductive effects happening with the ketone and the aldehyde. So with the ketone, the methyl groups are slightly electron donating. So electron donation makes that a little bit less reactive. Comparatively to the aldehyde, where the hydrogen is very slightly electron withdrawing. So that's why the aldehyde has a little bit more partial positive character on the carbonyl carbon, making the aldehyde more reactive than the ketone.